My name is Juncheng E from European X-FEL in Hamburg. So now my current job is to conduct experiment-related simulations and develop and maintain the SIMEX simulation workflow for PaNOSC. And at the same time, for the PaNOSC work package 5, we are developing a uniform API called Vinyl to integrate both the photon-related simulations and also neutron-related simulations. Simulations are quite important for the experiments. There are two key benefits. One is to help the users to plan the experiment before the actual starting of their beam time. They want to do some simulations for the X-ray source fluctuations and optics setup, and also radiation damage to the samples and the detector geometry and detector responses. They are all important for their experiment. And for each step, we now have some softwares. For example, for X-ray source fluctuations, we can use fast code to do the simulation. And for the optics, we have WPG and SRW for the wave propagation simulation. And for radiation damage to the samples, we have XMD code and GROMAX code for the ionization simulation. And also for the detector geometry and the detector response, there is the Gen 4 code to do this kind of simulation. And with these simulation tools, the users can plan their experiment before the actual starting of the beam time. And also the other important aspect is to help users to interpret their experimental data after they collected their data, especially in ultra-fast dynamics researches. When the event is very short for the researchers, maybe they only capture the start and the end status of the event. In the middle, they must implement some simulations to help them interpret their data to have a better understanding of what happened. SIMEX is a uniform API written in Python to help users to organize their start-to-end simulation for the photon experiment, especially for X-FEL experiments. One would like to know from the source and until the end of the response of the detector. So in SIMEX, we can organize the start-to-end simulation using the previously mentioned packages to do it from the X-ray source, and then we propagate it through the beamline and do the photometric interaction simulation, and then simulate the results you got from the detector. And the benefit of it is to have a easy way to organize the simulation, and also it can make it easier to run this kind of simulation on a web service. So you don't have to install a lot of softwares by yourself. You just need to open a web page on your browser and submit your job on it. Today I will show you two demonstrations for SIMEX. One is about serial crystallography and one is about single particle imaging. The first one is a serial crystallography simulation. So we will simulate the final diffraction data collected on the Egypt detector, which is used a lot in the SPB beamline at European X-FEL. So first, we just import some of our necessary modules from SIMEX. set up some environmental variables and set up your diffraction data output path. And then you can set up your beam information, like your photon energy, how large is your beam, and what pulse energy you have for your beam, and photon energy divergence, and so on. And you set up your beam, and you set up your detector. The detector, it has a lot of separated modules, so we have a preset of this module. You just need to import it, and then you give this geometry file out. Then the SIMEX calculator will read it later. So then we can set up the diffractor. So it's like now you know what beam, what photon you have. You know what kind of detector you have. You just let your diffractor know what sample you have and how would you like to operate your experiment. Like, do I need to rotate my sample, and how many diffraction pattern do I want to collect, and do I want to simulate the detector response with a Poisson noise. And then after setting up this, you can run the diffractor back engine. Then the diffractor can export the data into HDF file, and then you can use some data analysis code to read it, to analyze it, or to, if you have some data analysis workflow, you can use this simulation data to validate your data analysis workflow. So this is the first demo. Then we can go to the second one. It's about the single particle imaging. So we do the similar things. We will import our simulation modules, and then the same, we set up the photon beam, what energy we have, the beam diameters, pulse energies, and also we set up our detector. Here we set up not that complicated detector, only a single panel detector, and we do it here. And then the same, we tell the diffractor how many diffraction patterns we need. Do we need to rotate our sample, something like that. And then we just run the diffractor back engine, and then you can save the output in HDF5 format. And then you can run some data analysis code provided by SIMEX. You can show the diffraction pattern, get the resolution rings, and plot the radial projection and the function of Q. And then the photon statics for each pattern you have. And you can also export the data into a NumPy array. So then you can use some other Python tool to analyze your data. So that's it. Now we are creating more examples for our users to get more familiar with the concept of this kind of start-to-end simulations, to make them quickly find what they need. And also, we are collaborating with Work Package 4 in PaNOSC to get the data exported in Nexus format. which will be used as a golden standard for the data analysis packages developed in the framework of PaNOSC. So then when they want to test some of their data analysis workflow, they can, and also they can get benefits from the data if they want to do some machine learning based analysis methodology, because for that kind of method they need a lot of data to train their algorithm. The easiest way is to go to our GitHub webpage and to submit an issue on that page, and then we can have a discussion on that topic. And the second, of course, you can just contact me directly through email address. So I guess that's it. Thank you.